All right, today we are going to crack open the National Electrical Code. Yeah, I know, sounds dense, but we're going to uncover this brilliantly simple rule that keeps our modern buildings powered up without, breaking the bank or the entire grid.
I mean, seriously, think about it for a second. Every single desk has a computer, probably a monitor or two, a phone charger. You could have hundreds, maybe even thousands of outlets in just one building. So how on earth do engineers actually plan for that kind of load? Well, it's not magic, that's for sure. It's actually a really smart, super practical piece of electrical engineering. It's written right into the code, and it acknowledges a simple truth about how we really use electricity. This one little rule saves builders millions and millions of dollars, all while keeping us totally safe.
Okay, so to really appreciate how great the solution is, we first have to wrap our heads around the enormous problem it's trying to solve.
Just imagine for a minute if you had to design an electrical system for the absolute worst case scenario. We're talking every single device in the entire building plugged in and running at full blast, all at the exact same time. Now, is that theoretically possible? I guess. But is it probable? No way. Not even close.
So if you actually calculated the load based on that, let's call it a worst case fantasy, you would end up with a truly massive number. For a pretty normal sized office, you're looking at a potential load of something like
50,000 voltamperes. That's the unit we use to measure the total electrical load. And as you can imagine, planning for that much power, just in case, that has some pretty serious consequences. You'd need absolutely giant wires, huge electrical panels, massive transformers, the whole shebang. It would be incredibly expensive to build and just wildly inefficient to run day to day. There just had to be a better way, right? And thankfully, there is. This is where the National Electrical Code comes to the rescue with this really elegant answer. And it's an answer that wasn't born from theory, but from decades of looking at real-world data and just applying some good old-fashioned common sense. It's a concept called a demand factor. A good way to think about it is like a highway, right? We don't build highways wide enough for every single car in the city to be on it at the exact same time during rush hour. That would be insane. We build it for the probable peak traffic. Well, a demand factor does the exact same thing, but for electricity. I absolutely love this way of putting it because it perfectly captures that shift in thinking. We're not designing for some 1 in a billion electrical apocalypse. We're designing for the normal, predictable rhythm of daily life inside a commercial building. So where do we find this magic rule? Well, it's laid out right here, plain as day, in Table 220.47 of the National Electrical Code. Now, the code is super specific here. This shortcut is meant for places like offices, stores, and schools. Basically anywhere that isn't a house or an apartment. Places that have tons of outlets that are only used some of the time. Okay, now what's really interesting is how this rule actually starts. The code is still pretty conservative. It says, for the first chunk of the total electrical load, specifically the first 10,000 volt amps, you have to account for all of it. 100%. So there's no discount right off the bat. But here is the really clever part. For everything, and I mean everything, above that initial 10,000 VA, the code lets you apply a demand factor of just 50%. It's basically a calculated bet, based on mountains of data, that you're probably only going to use about half of the remaining available power at any given moment. And look at this. It's so simple. This table illustrates the entire rule in just 2 lines. The first 10 kVA, you take it at 100%. Everything else? It gets a 50% discount. It's simple, it's powerful, and it's incredibly effective. All right, Siri is great and all, but let's actually see how this plays out with our hypothetical 50,000 VA building. Come on, let's run the numbers. Okay, so we start with our big potential load of 50,000 VA. The first 10,000 of that is counted at 100%, so that's 10,000 VA right there. That leaves us with a remainder of 40,000 VA. Now we apply our 50% demand factor to that remainder, which gives us 20,000 VA. So you add the two parts together, and our new, much smarter load is 30,000 VA. Just like that, we've cut our required capacity by a massive amount. And we didn't do it by guessing. We did it by applying a time-tested, data-driven rule straight from the code. And just look at that difference. It's huge. We went from that intimidating potential load of 50,000 VA all the way down to a calculated demand load of 30,000 VA.
That is a 40% reduction. You can see right here on this chart just how incredibly impactful this one simple table really is.
So, what's the big takeaway here? Well, the crucial point is that this isn't just some accountant's trick to save a few bucks. This is really fundamental to good, intelligent engineering.
This rule strikes a perfect balance. It keeps us safe by making sure the system can handle realistic peaks, not impossible ones. It boosts efficiency because you're not running all this oversized energy-guzzling equipment. Of course, it creates huge economic savings on materials and construction. But I think most importantly, it represents intelligent, data-driven design. It's a rule that has evolved over decades to perfectly reflect how we actually live and work. And behind all the dense text of the National Electrical Code, there are hundreds of smart, practical rules just like this one. They're all working together quietly to make our buildings safer, more efficient, and more affordable. It's like the invisible framework that makes our whole modern life possible. It really makes you wonder, doesn't it? What other invisible rules and brilliant calculations are just humming along in the background, shaping the world we live in every single day? Something to think about. Thanks for tuning in.